we are extremely happy to be able to host a talk by Professor Fazle Hussain, Texas, and Yao on the physics of vortex reconnections and turbulence cascade. Fazle, to you. Thank you.
Thank you. This is Fazle Hussain at Texas Tech University. Is in a small city in Lubbock, Texas. I will initially give a short introduction followed by detailed topological studies that will be reported by my young colleague Jay Yao. So initially I will give a brief overview of the long journey that I personally had in turbulence, starting with turbulence physics, how we came across vortex dynamics, and then the role of vortex reconnection in a turbulence cascade, which is by far the most complex part of turbulence, which is also considered to be the most difficult part of physics, not only classical physics. In this next slide, I say that there have been three rather distinct approaches to studying turbulence: statistical, structural, and dynamical. Different people focus on different areas and view that their area or their approach is the right way to study turbulence. We therefore spearheaded the structural approach, but the essence of turbulence, the truth lies quite equally to all these three, and we have actually studied in all three aspects. Now, research over the recent decades have conclusively established that underlying the apparently random motion called turbulence, there is a hidden order, and we call it coherent structures, and I have always used this as a study of order within disorder. Normally we usually look for disorder within order, and it has been clearly demonstrated that it is indeed possible to achieve turbulence management, namely both enhancement and suppression of turbulence phenomena, enhancement like heat transfer, suppression like drag and noise and so on, through generation, growth, interaction, and decay of these structures. For years, people were dubious about whether there is really a coherent structure in turbulent flow, and my answer was with a simple example of a fully turbulent elliptic jet coming out of an elliptic hole, and the jet axis flips-flops the turbulent jet. And if there was no coherent structure, this will not be possible. Indeed, I then concluded that it is impossible to control turbulent flow unless there is coherent structure, and made rather controversial claim, no coherent structure, no control. And indeed, many people may still be trying to control turbulent flow without recognizing that they are really controlling turbulence through the mechanisms involving the underlying coherent structures. The studies of coherent structures are indeed very significant, not only for understanding the fundamental physics, but also the modeling of turbulent flow, and also in the applications like heat and mass transfer. So therefore, controlling entrainment and mixing, chemical reaction like combustion, which is very important in many power devices, auto engine and so on, momentum transfer, namely drag control, and also controlling noise production. You see, in modern days, in air-conditioned room, you don't hear air conditioning sound because the organized structures are suppressed. But if you're in an old building, you can hear the air conditioning sound. So indeed, the coherent structures are indeed the muscle and the voice of turbulent flows, because coherent structures are the ones who do most of the dynamical things and also produce sound. Now, the overwhelming majority of studies, even today, are based on flow visualization, which is not only misleading, but quite often incorrect. And many people don't realize it. The explanation is very simple. When we study turbulence, we are actually studying random vorticity fluctuations. So here is a simple equation controlling vorticity transport. And if you use dye or smoke, this is the corresponding equation. One thing you notice that within the flow, vorticity can be augmented by itself through 3D stretching, which is absent in scalar. Therefore, what you see via scalar field is not what is happening in the flow. Like you can puff a smoke ring and release, and you see the smoke ring propagating, but you can be sure the vortex is not soon has left the smoke pattern. So you're watching the passive smoke pattern. So therefore, in the idealized case of two-dimensional flow, of course, turbulence can only be three-dimensional. But if you close your eyes and say it's two-dimensional, then also the two fields will be similar. That means by watching the dye or smoke, you are really watching the vorticity pattern only in the singular case of the Schmidt number being 1. That means the vorticity diffusivity, which is nu, and thermal diffusivity or scalar diffusivity, kappa, are equal. Only in that case you are watching correctly. If not, particularly in 3D flow, the two are distinctly different. And therefore, dynamically significant events happening in a fully turbulent flow are not observed. What you are not observing the most dynamically significant, because wherever the vorticity is high, the marker is depleted by stretching. And therefore, by visualization, you may be missing the most important part of turbulence. So the first time this was conclusively demonstrated by supercomputer simulation of two colliding vortexing. Here, left-hand side, you can see both the vorticity contour and right-hand side scalar contour. You see, for a short time evolution, they look similar, but further down, you see they're quite dissimilar. So therefore, quite often, opinions or conclusions drawn from flow visualization can not only be limiting, but can be incorrect. And this effect of if the flow is three-dimensional, the typically Schmidt number is of the order of 6,000. But even if it is 1, if it's not, even if it's 1, the two evolve differently and the departure increases with increasing time. So we do need to characterize coherent structures. What is coherent structure? It is the underlying organized vorticity, which is also time dependent, but is underlying the random vorticity. So if you see my hand, I don't know if you can, if you have random vorticity, but underlying there is an organization, or two patches of vorticity, they're randomly moving, but underlying there is a coherent motion. That part is coherent vorticity. And the remainder is incoherent turbulence. So we therefore need quantitative study, not visualization of coherent structures, both in measurements and numerical simulation. And then we extract the coherent structure from the incoherent part. And this is what I call finding order within disorder. the tremendous machinery developed for understanding, studying these kind of flows from a variety of experiments, jets, pipes, bound layers, mixing layers, as well as numerical simulations was presented by me in this meeting in '83 in Kyoto, and this was summarized in the book edited by Professor Tatsumi. So as a result of this drive for definition, we came up with a definition of the lambda 2 definition, which was prepared by Zhong, and right now it is extensively mentioned in literature and without reference as if it is a standard knowledge. Now, if you look at a jet, there initially you have organized structure and then appear fine scale turbulence. So if you idealize, the jet initially forms a vortex ring, and somehow the vortex gets deformed, and there is a puff of turbulence, and there is a noise radiated which can be very high if the speed is high. So I speculated in 70s that there must be this vertical structure must form lobe, and since velocity is higher in the center, they will form lobe structure like this. This can be 5, 7, 9, and these parts will touch, and therefore they will undergo reconnection, and therefore this single lobe will break into a series of lobes, and the breakdown process is the cause of aerodynamic noise generation. It turned out it took us 40 years, and only recently Hamid and Jean-Pierre Hickey, collaborating with us in Canada, have produced. The first paper was published in PRF last year, and the second paper is going through final revision review on this, and will not talk any further. So we did succeed in showing that it is indeed reconnection which produces most of the sound in jets. And we also speculate the elusive phenomenon of crackle noise in jets is also produced by reconnection. This was my speculation 40 years back. All these years, no one proved I was right, but no one was able to prove, even though many have tried, that I was wrong. So it still remains an open question, this arrow, the blue arrow. Now, what is reconnection? Now, I'll go fast. If you have two curved vortex filaments of opposite sign, if they come by self-induction, they collide, and at the contact point, the vorticity is opposite, so they cancel each other. So you're left with a lot of vortex lines. The vortex line cannot end within the medium, that they cannot reconnect, and therefore form two vortex filaments, which is half red and half blue, whereas initially it was all blue or all red, and they move in further apart. And of course, there is a little bit left. It is never complete. We'll come to it. So this is the essence of reconnection. This is clearly a topological transformation. So vortex reconnection is a fundamental topological transformation event. And so this is a way also for many coherent structures to break down, especially since the turbulent shell flow consists of many vertical coherent structures. This we claim as the essence behind most turbulence cascade, mixing, and aerodynamic noise generation. We will discuss only cascade. And also, this has been used and is a very fertile approach to study finite time singularity, in which Jay has written some papers, and Moffat and Kimura and Tom Howe have written papers. So you see, this is a typical trailing vortex of an airplane, and it can break up under proper atmospheric conditions by growth of waves into vortices, and more clearly illustrated here. This is a picture. Now, in a viscous flow, this reconnection, two rings collide as we showed but finally form another two rings going in other directions. But it is never complete. A part of the vorticity is left connecting the two. So this is why viscous vortex reconnection is extremely complex, whereas in case of quantum fluids, the reconnection is complete and there is no thread or remnant left. No wonder many more papers have been written in quantum reconnection than in viscous reconnection. Typically, we study in simple geometry like colliding rings or two rings offset. We can also see reconnection between two orthogonal vortex rods. So what you notice that by mutual induction, the rods become locally anti-parallel. And similar studies have also been done by collision of dipole. You need dipole so that a rod does not move, but if you have a dipole opposite vorticity, it will move and they can collide. So other people have studied. So we narrow down to now two parallel elements. Since any arbitrary orientation of two adjacent filaments, as CGS showed, become locally anti-parallel, then this is the fundamental flow element to study vortex dynamics. Reconnection, and this is what we have used and many others, and pretty much since then everybody, including Shelley and Orzag and so on. So the initial condition you have is sinusoidal anti-parallel vortex filament at an angle. By self-induction, they bang into each other and undergo reconnection. And we'll show a movie. There are two planes. One is, this is the symmetry plane. This is the collision plane. That means this is the plane to which the two vortices collide. Of course, we are considering symmetric situation to understand, but in asymmetric situation also the basic mechanisms remain the same. Now, one important thing we always study is circulation, the area integral of vorticity. It turns out circulation has the same dimension as kinematic viscosity. So circulation of a vortex divided by kinematic viscosity is the vortex Reynolds number. Now this is the first study of this subject that Melander and I made in CTR1. You see initially the two vortices are anti-parallel, and because of mutual induction they bang into each other. As soon as they touch, they neutralize each other, so the vortex lines connect and pile up at these two places we call bridge, and the part inside is thread. And you see, even after significant enhancement, where there is significant transfer of vorticity from the symmetry plane to the collision plane, so there is still quite a bit of vorticity left, and this we call thread. And of course, these two vortices pull apart by their curvature. So right now, because of induced velocity, the threads are pushed down. They stop reconnection because they don't bang into each other anymore. But as these two rings, new formed rings, move further apart, then they reverse the curvature by mutual induction. And then there is a next vortex interaction. At that time, we speculated. And later we show. So right now you can define three characteristic times when the vortices are approaching. So this is the mutual induction, and then bridging. During bridging, this vorticity realigns from along the axis to orthogonal to the axis. So therefore the circulation decreases. So this is the bridging part, and during this time, the remainder left is threading. Now here we show at a higher Reynolds number, and we show by two different colors how the two intermingle and form some interesting overlap region, which is not so simple. It has many laminations, and depending on Reynolds number, this is only at 2000. Some interesting structures develop. Now, if you take the time for the circulation to drop as the as the reconnection time, then you can see the reconnection time scales as Reynolds to the power minus 3/4, and the rate of reconnection you see as the Reynolds number increases, reconnection happens faster and faster, also scaled as Reynolds to the power half. So this was our computational result. Now Ni, along with Shi E. Chen from Peking University in Beijing, did a theory, and he found that this scaling actually continuously changes from -1 to -half as the Reynolds number increases. This is an analytical study. Now coming back to getting to the details of the structures, you see with increasing Reynolds number, the fine scale structure increases and the complexity increases. They survive longer because the Reynolds number is faster. The vortices stretch, and so the vortices survive for a long time. Now, in between these two bridges, there is two sheets of vorticity of opposite sign. So the peak vorticity head from the left pulls the peak vorticity out ahead and vice versa. So immediately you form a head-tail structure. So therefore the head progressively moves faster and faster than the tail, and so at the beginning and during the tail is like a plane jet. Therefore it is susceptible to antisymmetric instability and form series of vortices in the form of dipoles, which you'll see later. Now this comes our hypothesis we made 88, that once you have reconnection, the bridges push the left or thread down, and as soon as you reverse the curvature, they move away from each other, stops reconnection. But when these rings move further apart, then by mutual induction of the threads, they reverse the curvature. And there comes the second reconnection. Again, the second reconnection forms a second set of vortices. They're moving apart, but pressing the remainder threadlet to reverse curvature and stop reconnection. But as they move further, by their mutual induction against reverse curvature, have the third. So this was our imaginary perception of the role of vortex dynamics and reconnection in turbulence cascade. As you know, there is no viable physical mechanism of turbulence cascade yet, and we felt this is the most likely possibility, since turbulent flow consists of many vertical structures. Turbulent flow is basically a tangle of vertical structures. This must be going on continuously, and therefore this is the underlying mechanism of cascade. Even though some structures may interact and also pair, that will be inverse cascade, and we have evidence for both. Now, how do you go to left? This movie goes fast, but I want to stop for it. Anyway, that's fine. Let's just go ahead. So we have two counter-rotating vortices. They have the right rotations. So we have two planes. One is symmetry plane, one is collision plane, which is mnemonic. And we see all the circulation initially is in the symmetric plane. Eventually, most of it will go in the collision plane. And here is the animation. This is the vortex surface. In many cases, you see this is the circulation is constant. They are coming close to each other. As soon as it starts, there will be circulation transfer, and it will very rapidly evolve the three-dimensional structure at this interaction region. And you can see from this structure, you get very fine structures depending on Reynolds number. this structure details will be quite different. This is for 9,000 Reynolds number. By the way, 9,000 was pretty much the limit of simulation until about 3-4 years back. That was the limit of computer capability. But Jay was able to push it to 40,000, which will show next. And you can see with 9,000, there are fine scale. These are the dipoles. And also some of the dipole can interact to form rings and bridges, local bridgelets. And you can see the rich structure. So these are definitely strong topological transformations. Do we continue? Yes. Sorry, I didn't quite time which picture goes when. So you can see the details. Behind a 747, a 1 mile by 1 mile flow, this might be like a millimeter. So you can see the scale variation. These are of the order of millimeter or less. So the 40,000 again continues. And you can see formation of very, very, thousands of fine structures. This is not hash or noise. This is real structure. You can see through this. And as you let it grow more, you see that the threads are wrapped around the bridges. And the very fine structures are clearly visible. You can see this part, how all the fine threads are still there. In the middle, there is a continual reconnection and formation of rings and hairpins. And sometimes the threads are wrapped around by circular vortex, fine scale circular vortex rings. So you see the portrait of reconnection can lead to what we call avalanche. These structures appear very abruptly, but this is a combination of formation of rings, hairpins, and so this we call is the underlying physics of cascade. Until now, it's always used as hand waving, or Kolmogorov used big eggs and little eggs, but turbulence are not big eggs and little eggs. Thank you. I really invite now. I don't need the publicity. Dr. Jay Yao is a thriving, brilliant scholar, and he has done more work, which is going to talk now. And I appreciate Rika and the committee for allowing us to share so that he can get to show and get the appropriate visibility that he can benefit from. Dr. Yao, please.
Okay, I'll go to continue our talk. Let me share my screen here.
If you want to ask any question, fine. If not, time is the issue.
I think that if you have questions, then you can ask questions before we go to the second part. If not,
okay, Fazle, I have a very simple question for you, but is a recurrent question to me, and so I'd like to hear from you. So this anti-parallel mechanism, is this generic, or you
Yes.
say that is common, but you can also see different angles of reconnection?
Yes, we have done. If you force two orthogonal vortex rods, they will collide, or two dipoles. But if you look locally and magnify, they're locally formed by mutual induction anti-parallel configuration. This was conclusively demonstrated theoretically by CGA.
I do remember a long time ago was a very interesting race, and I remember that Zabusky started with, and Peltz, of course, they started with orthogonal configuration, but they observed that very locally, so to speak, the reconnection goes anti-parallel, isn't it?
Yes.
Yeah.
Yes, but to my knowledge, Norm also did, but Eric CGA also showed it. I think he cited more.
Fazle, since we know about this a long time now, is there any analytical discussion or at least attempt to prove that this is generic?
I think CGI's work is about the best. Jay, if you know anybody else, CGI's work is about 25 years old.
I know
Okay,
some
thanks.
of the work, even in quantum cases, they have shown that no matter what the initial configuration, even vortex node or link, it should become anti-parallel before reconnection. But the angle between the anti-parallel structure depends on different initial conditions, not generic before reconnection.
And Eric will show in his slide some which are not necessarily anti-parallel.
Okay, thanks.
He has some other papers published, orthogonal vortices, and a rod going through a ring. And those are not, I mean, globally anti-parallel, but locally, if you magnify, you see anti-parallel effect. Okay?
Yeah, okay, thank you.
Okay, maybe we can continue the second part.
If you have time, we'll have more discussion, no problem.
Yeah. All right. Yeah, I'll continue the second part of the talk, which is about the dynamics of viscous vortex node and link. Let's first give some. Let me first give some brief introduction on helicity. Helicity is the Warning integral of the scalar product of velocity and vorticity, given this equation. Yeah. In addition to energy, helicity is also image invariant, means it's the invariant of all equations. Based on the Newton theorem that conservation laws and symmetries are at the heart of the physics and determine the evolution of the system. For example, in 2D turbulence, that we have two image invariant with one is energy, which is the Warning integral of velocity square, and another one is entropy with Warning integral of entropy square. Due to these two image invariant, that it will cause the flow to have two dual cascade, which means that energy will cascade to inverse cascade to large scales and entropy will cascade to small scale. Question will become like, since we have another image invariant in 3D turbulence, 3D flows, how the helicity will affect the flow dynamics and energy cascade. The importance of helicity are underscored by the growing importance of the vortex node and links, which can be also important in other flows such as biology and plasmas. Helicity has a topological interpretation as a measure of the link and the knotedness of the vortex line in the flow. Helicity can be geometrically decomposed as this form, as most readers know that here that gamma is the circulation of the vortex tubes, and LKIJ is the link between vortex I and vortex J. WR is a rise, and TW is a twist. And we also know that the twist can be further decomposed into two components. One is torsion twist, that's the torsion of the vortex center line. Another is intrinsic twist, which is how the ribbons wrap around these vortex center lines. For all these quantities, link, rise, torsion twist can be measured based on the vortex center line. But intrinsic twist, which requires some additional information of the vortex line in the core. So typically in viscous flow, the intrinsic twist is very difficult to be measured. Let's first consider a simple vortex, which is a bachelor vortex, or an Hussain vortex with actual flows. The vorticity distribution is given as this form. Here, omega r, omega theta, omega z are the radial, azimuthal, and actual vorticities. Here, Q quantifies the strength of the actual flow. If Q is equal to 0, this is no actual flow, it means it's Hussain vortex. If Q is infinity, that is like a circular jet. Here, that which shows the evolution of dispersion of entropy, which can be given as this form. When it is equal to minus 2 mu omega divided theta square when Q equals 0, which is Hussain vortex case. And the magnitude of this dispersion of entropy will continue increasing as Q increases. It becomes minus 4 mu omega divided sigma square when Q equals infinity, which is a circular jet cases. As we also know that in 3D periodic domain, the energy dissipation is equal to mu omega. So the rapid dissipation of entropy means that as Q increases, the energy dissipation will be suppressed, which is consistent with long-term claim that helicity will suppress energy cascade. And the helicity evolution is given here. Here, the helicity is mostly the twist helicity. It's equal to minus 2 mu ornithical omega dot delta cos omega. Omega dot delta cos omega is also called super helicity. It can be further simplified as here. So it will depend on the initial helicity, viscosity, and the core size. Here, theta is core size here. So for small core size, the dissipation of helicity will become more rapid. So it's always assumed that for very single vortex, the dispersion of helicity, particular twist, will be very rapid, so that twist will have limited contribution to helicity. Yeah, although our main talk will focus on the viscous vortex not a link, I must mention that a lot of works on quantum vortex not a link. Here are some of the reference that I know that Professor Rika is one of the experts in this field, that he published a lot of important papers in this subject. The study of viscous vortex not dates back to 1987 when supercomputer became available to study vortex reconnection. Yeah, Kita and Takota performed the first DNA simulation of vortex knot. They observed that helicity will decay after reconnection, but the rate of decay will decrease with increased Reynolds number. So this makes them to speculate that helicity may remain conserved at high Reynolds numbers. The study of vortex knot and link in viscous flow didn't draw too much attention until a recent work by Professor Ivan at University of Chicago. They experimentally created vortex knot and link in a water tank, and they using high-speed scanning tomography, they measured the topology evolution of this kind of vortex knot and link. Most importantly, they found that helicity, even in viscous flow, can remain conserved. As we show here, we show some results from their paper. We find that here the blue dot is the raw data, and the orange dot are the smooth data. You can find that even for the Truffle case and for the vortex link cases, that helicity remains almost conserved during the evolution, during this kind of unlinking, untying, unlinking process. But one thing we don't comment that their results are obtained based on major rise and links, which is based on tracking the air bubble in the water. But they cannot directly measure the twist. All the results are obtained by assuming that the twist will be rapid decay due to viscous dissipation. And inspired by this experimental work, there are a lot of numerical work recently to study the vortex knot and the links. And the main question in this subject is that, is the helicity really conserved in viscous flows, particularly at high Reynolds number? And how will the helicity convert between one form to another form during this kind of unlinking and untying process? To address this question, that we have performed some simulation at relatively high Reynolds number. Here the initial condition we used. The parametric equation is given as here. So for Truffle knot vortex, P equal to 2 and Q equal to 3. Here for the mean radius RT, we choose as 1. Lambda, which quantifies the ratio of the inner small radius to the mean radius, which is at 0.5. The vorticity is initialized based on the algorithm developed by our colleagues at Peking University, Professor Yue Yang. The vorticity distribution in cylindrical can be given here. Here ES is the ES, E low, E theta are the axial, radial, and adjacent directions. And the first component, which in the axial direction, is mainly associated with the rise helicity. The second part is mainly in the adjacent direction, is associated with the twist helicity. The advantage of this initialized algorithm is that we can arbitrarily turn the tau to change the intrinsic twist, so that we can obtain a vortex knot with arbitrary twist. In this study, that we are making our intrinsic twist to be the negative of the torsion twist. Based on these parameters, our rise equals 3.52 and torsion twist is 2.48. So the total sum of the self-link, which is rise plus torsion twist, is 6, because they have some additional streaking structure there. So let's first look at the videos to show how the evolution of a vortex knot evolves in the viscous flows. The vortex knot will move upward, and they will rotate counterclockwise as it moves upward. And they will become bended anti-parallel and reconnect to form two separate rings. We will call the top ring the small leading ring, and call the bottom ring large trailing rings. These rings will continue going upward and rotating counterclockwise. Let's further look at the evolution at high Reynolds number. You can see that at high Reynolds number, the evolution is quite similar to the low Reynolds number. But difference is that there are a lot of small-scale structure generated, what we call thread. And this is the main difference between quantum case and the viscous case, because as Fazle said previously, that in viscous reconnection, this kind of reconnection is never complete. There will always have some thread left behind which connect these two rings, and it will become weak due to viscous diffusion, and cannot be visualized at this region. Another important interesting feature is that although initially helicity density is almost positive, like as red color, but you will see that during evolution and after reconnection, that we have some negative helicity density, which is blue color show here, develops. Let's first look at some this here. We further provide a qualitative comparison between experiment and the DNS result. The DNS result is performed at Reynolds number 12,000. As you can, one difference between experiment and the DNS is that for experiment, that this vortex knot are perturbed, so that there will be one reconnection at a time. But for DNS, the this is highly symmetric, so it 3 reconnections at simultaneously at the same time. Yeah. Another difference is that at higher number DN simulation, there are a lot of small scale structure as we showed previously generated. They're wrapped on the thread and wrapped on the bridge. This vortex rings and there are some thread left. Yeah. But the overall dynamic is quite similar. That after the connection, vortex knot will form 2 separate rings. Let's first look at some flow statistics. This is the first we showed entropy, which is the Euler integral of the vorticity square. Yeah. It will decay initially, and the decay rate will decrease with Reynolds number. Here, that red is Reynolds number 2000, and the black is Reynolds number 12,000. Here, you can see the decay rate is more or less like follow the model developed based on the bachelor vortex with a dashed line. And then during the connection, that entropy will increases, and the rate of growth will increase with Reynolds number, and the time for the peak to occur will slightly decrease with Reynolds number. This is because the reconnection will happen earlier at Reynolds number. After the connection, the entropy will decay. But this time, the decay rate will be increased with Reynolds number. It means that Reynolds number decay much faster. This is because during the connection at Reynolds number, there are a lot of small scale structure generated. Their dissipation will cause it can rapidly decay at Reynolds number. The right figure shows helicity. At the initial time, that helicity almost remains unchanged, and it will slightly decrease before the connection. And during the connection, that rate increases, and the rate of growth will increase with Reynolds number. After the connection, the evolution is quite dependent on Reynolds number. For small Reynolds number, the helicity will decay. But for this Reynolds number 6000, helicity will steadily increases. And for even higher Reynolds number, it will increases and saturate. And the peak value is about 1.5 times the initial value. And also, we also want to mention that although the helicity seems to increases for this Reynolds 6000 cases, it will eventually decay. This will be confirmed for this long-term evolution. You can see here that at t equal to around 11 seconds, the helicity will decay. But this kind of transient growth of helicity is very interesting, and we expect that this kind of transient growth will increase with Reynolds number, and this will suggest that helicity is not conserved in viscous flow, which contribute to many previous results. And the question will become answer why helicity is not conserved during reconnection and after reconnection. Before that, let's first look at the evolution of vortex center lines. That what we want to comment on that vortex lines are not always along the vortex center lines for viscous cases. So vortex line cannot be used as a representation for vortex core center lines. There are many, like in viscous flow, how to extract vortex center line is still open question. There are many methods proposed. Here we are using the method based on the normalized helicity density, which we are assuming that within the core, the angle between the vorticity and the velocity is minimal. Here we show that extracted vortex center line result based on this method. You can see that you can well capture the evolution of vortex knot and the vortex rings after reconnection. Here the color is the velocity tangential to the vortex axis. Based on these extracted vortex center lines, that we can have calculate several important quantity. The first is the length. The red blue dot is for the vortex knot before reconnection. The yellow is for the small leading ring after reconnection. The red is for the large trailing after reconnection, and the purple square is the sum of them. You can see that before reconnection, the length continually increases until slightly decrease during connection. And after reconnection, the length for the small leading ring and large trailing ring become almost constant. So the sum is almost remains constant. Another important quantity is the moment of vorticity, which can be related as an impulse, which is the Euler integral of x cross omega dv. For very thin vortex core, we can replace vorticity as U circulation, so we can obtain this very simple equation. Moment of vorticity equal to gamma times s, as is defined here. It provides a geometric way to calculate moment of vorticity by calculating the area enclosed by this vortex axis projected to certain planes. I think that Professor Rika also have some similar work on quantum cases. In our cases, that all the other two components are zero. They only have it's non-zero only for the z direction. So it's only for the last component it's non-zero. We show the evolution of the S3 as a function time. You can see that it remains almost constant. It suggests that the moment of vorticity is conserved. But interesting, we find that S3 for the small leading ring increases and S3 for the large trailing decreases. Because that after forming two rings, that the small ring are being stretched by the bottom ring, and the bottom ring are being compressed by the top ring. So that is why that area for the small ring will increases and area for the large ring will decreases. Then let's further look at the rise for the first look at rise for the Reynolds number 2000. Yeah. Here again, that the symbol is for the blue symbol is for the vortex knot before the connection, and the yellow and red are for the small ring and large ring respectively, and the square is the sum. Here we provide the helicity gamma square as a reference. We can see that before reconnection, helicity the rise decreases, and you have a big drop during reconnection, but it still continues. And after reconnection, it's almost saturated, like it becomes constant. This result is very consistent to what has been observed for quantum cases. And we also find that small leading ring, the rise for the small leading ring decreases, and the rise for the large trail ring increases. Again, it's because that during this kind of process, the small leading ring are being stretched, and the larger trail ring become compressed. During this kind of stretching and compression, you have a conversion between rise and twist. Once it are being stretched, the rise will convert it to twist, so rise will decreases. Let's look at the rise evolution for higher number, which tells us that the red dashed line is the reference line for the lower Reynolds number. It's interesting we can find that different from the helicity, which is the solid line, that rise is almost unchanged for Reynolds number. It means that for different Reynolds number, the evolution of rise is almost the same. So let's further look at the general for the twist. As we know that in viscous flow, it's very difficult or sometimes impossible to directly calculate the twist. And so that based on this kind of helicity decomposition we showed previously, so we can define what we call general twist, which is equal to h divided by gamma square minus rise. It's equal to twist at the initial time, and it can be served as good approximation for twist at later times. We can see that the general twist continues to increase before reconnection, and during reconnection there's a sudden jump, and for the small leading rings become negative and continue increases, and for the top rings positive and continue decreases. The sum slightly decreases with time. And this is for higher Reynolds number. You can see different from rise that twist will be quite different from different Reynolds number, particularly after reconnection. For small leading rings, they become more negative. For the large trail rings, become more positive, and the total twist will increase with time. Which is consistent with the helicity. It suggests that the previously observed increase of helicity is mainly due to the twist. And also we find that this kind of twist is very general twist. It very depends on Reynolds number. At higher Reynolds number, you have more twist generated. Then this figure further shows the torsion twist and the self-link. Like before reconnection, the torsion slightly increases, and we know that the rise slightly decreases. The self-link, which is the rise plus torsion, remains constant. And after reconnection, during reconnection, that torsion twist and the self-link abrupt jumps. So the self-link becomes 3 for the small leading ring and become 9 for the large trail ring. But we also need to note that calculated torsion is very sensitive to the inflection of the inflection point in the vortex center line, which is not very noisy, so you will see this kind of oscillation. But we can see it's quite consistent that if you have the self-link for the small ring becomes 3 and the self-link for the larger become 9. This is because that self-link this change discontinues through inflection point. During the connection, that we have developed 3 inflection points, so that the initial self-link 6 will become plus and minus 3 becomes 3 and 9. So this is why you have 3 and the self-link becomes 3 for the small ring and become 9 for the large trail ring. And we can also see that after reconnection, that the self-link doubles from initially 6 to 12. Right now we have summarized all the kind of helicity dynamics based on the topological aspect. Right now we try to explain the helicity increase based on the traditional vortex dynamics. The evolution of helicity density is given by this equation. The right-hand side has 3 terms. The first term is helicity production. The second is diffusion, the final term is dissipation. Interestingly, when you do a Wall integral, the first term, which production, and second term diffusion will go to 0. It means that although they have some production of helicity density, but the net helicity production is 0. It can be explained by using this diagram. Consider a vortex with a variation in the core size. In the small core size region, that we have high pressure, that you have pressure gradient. Also, in the small size, we can rotate faster. So initially, that parallel vortex line will become twisted. But the left and right hand side are twisted in different ways. So the left hand side and right hand side have different sign of helicity density. So you do have some helicity density generated, but the total sum is 0. So the helicity changes are mainly due to last term, which is dissipation, which is 2 mu times super helicity. Here we show the evolution of helicity density, helicity dissipation as a function of time for different Reynolds number. Before reconnection, that is slightly negative because during this process, as we showed previously, rise will come to twist will be dissipated, so this is why it's slightly negative. But we find that during reconnection, that HD becomes positive. It means that helicity will increases, and this kind of increase will increase Reynolds number. And after reconnection, that helicity density becomes negative for Reynolds number, but it still remain positive for high Reynolds number, which is consistent with the increase of helicity at high Reynolds numbers. So let's further look at the helicity density distribution in the vortex tube, and which is the top row, and the bottom row is helicity density. Helicity dissipation density, which is mu times super helicity. As we can see, that initially helicity density is mostly positive, but during the reconnection region, which anti-parallel region, they have some negative helicity density generated, which because in this case, this region that vorticity is going down is downward, but velocity due to mutual connection is upward. So this is why we have some negative helicity density generated. This means that reconnection, the vortex tube here becomes optically polarized, that with a different sign of actual flow, different sign of helicity. So after reconnection, that part of the ring here that become red, blue, and part of here become red, and also become, you can see here that different from what discussed by Fazle, that for symmetric anti-parallel reconnection, here the reconnection is asymmetric. So after reconnection, that the top leading ring become almost blue. It means that it's dominated by negative helicity density, and the bottom ring is mostly red. It's dominated by positive helicity density. So we can also, from helicity dispersion density here, we can show that the region with strong helicity density, we also have a very strong helicity density dispersion, but with the opposite sign. It means that helicity industry will be dissipated. But from this curve, that we don't know how the helicity density is positive or not negative in the whole volume. So how to quantify to quantify the negative helicity and positive helicity? We try to define a new quantity, which is H plus and H minus. H plus is the volume integral of the helicity, all the helicity density that's positive, which is denoted by this dashed line. H minus is all integral all the helicity density with negative helicity density, which is given by this dotted line. Here the solid line is the global helicity, just put here for reference, and this circle is just the negative minus H minus plus the initial value. So you can see that at the initial time that this circle collapsed with these dashed lines. It means that although there are some both helicity density generated, but the growth rate of H plus and H minus are the same. But during the connection, after connection, you can see that helicity density H plus is going to decay, H minus also going to decay, but they are decay at different rate, particularly at Hussain number. You see the difference become larger and larger. So this somehow gives an explanation why helicity increases based on this diagram. Let's summarize it here. Like initially, the helicity is positive, which is mainly corresponding to the rise. And during the initial evolution, that a same amount of positive helicity density and negative helicity density generated. So that if H plus becomes H0 plus delta H, H minus becomes minus delta H. But during the reconnection, that the negative one will decay faster. So that it will cause the total helicity to increase. This explains why that helicity will increase during connection. But recently, that Professor Carlo in Purdue give a more physical explanation on this kind of increase of helicity during connection, which is based on the anti-parallel reconnection of the anti-parallel reconnection. Consider two vortex segments as here. As we showed previously, that the helicity density evolution is given by here, which is approximately as 2 mu times super helicity. And we also know that circulation transfer can be given as this equation, that when we combine these two equations, we can get a simple equation as here. The change of helicity will be related to the vorticity perpendicular to that plane and times the circulation transfer rate. For symmetric anti-parallel cases, that the actual flow in these two vortex segments are the same. So there will be net with zero vorticity that perpendicular to that plane. So that this term will be zero. It means that for anti-symmetric cases, for symmetric cases, that there will be zero helicity increases. But for anti-symmetric cases, we know that the actual flow in the vortex tube will be different. So it will cause a non-zero omega z, which is perpendicular to that plane. So that it will cause helicity increases. And also from this equation, we find that the helicity increases were related to circulation transfer rate. So this is why explains why that helicity will increase more at Hussain number, because at Hussain number you have more rapid circulation transfer. So based on this explanation, we can explain why the helicity increases during connection. But another question we didn't answer is that why helicity will have different behavior for after reconnection, like for Lorentz number to decay, but Hussain number to increases. We know that after reconnection, the truffle knotted vortex become two separate vortex rings. So all the behavior after reconnection can be explained by using this kind of two vortex rings. And first, let's consider two simple axisymmetric vortex rings, which is optically twisted. So the total evolution helicity can be given as this equation. So that depends on the ratio of the two initial value of twist and divided by cosize. So the evolution of helicity will become quite different. Let's give an example. Like consider two optically twisted vortex rings here, that the inner ring are negative twisted with the initial twist equal to -9, and outer ring are positive twisted with the initial twist is equal to positive 10. At the initial time, that since the cosine is the same, but the initial value that positive one is much larger, so that the dissipation of positive helicity is much larger than the negative one. So this is why at the initial time that helicity decreases. But as long as this small ring move away from the big ring, that this small ring will under stretching by the big ring, and this big ring under compression by the small ring. This is doing leapfrogging. So due to vortex stretching, that the cosine of the small ring will decreases and the cosine of the big ring will increases. So it means that the ratio of this TWI divided sigma I squared will increases. It will be larger than the positive one. So that is why that it means that the negative helicity density, which is twist, will be dissipated more. So this is why the helicity will increases. For the same reason, at later time, that when the positive ring becomes stretched and the negative ring becomes compressed, that the positive ring will be dissipated faster. So this is why the helicity will decrease again. So during the different phase of leapfrogging, the helicity can sometimes increase and sometimes decrease. That depends on the ratio of the initial twist and their cosine. So this can be used to explain what happens for our coiled ring cases. But once you want to comment that our coiled ring case is much more complicated because the ring are coiled, you need kind of compression and stretching to additional rise and twist convolution. So for simplicity, we assume that the twist dissipation will follow this simple equations. Here, C is equal to mu divided sigma squared, which corresponds to the initial viscosity and cosine effect. Here, G, what we call is a geometric prefactor, which will account for the coiling effect. So from the initial figure of the twist, we can have some observations, because first that the twist for the small ring, initial twist for the small ring is negative, and the initial twist for the large ring is positive. Since the sum is positive, so the magnitude of the small ring is smaller than the magnitude of the large ring. We also have this kind of observation that the G for the small ring is larger than the G for the small ring. But then the total twist, the total evolution of the twist will be like that. So we can do explain both for the two rings they decay exponentially. But we can do a Taylor expansion of this exponential term. We can get a simple equation. After some modification, we can get this equation that TW is equal to delta TW at the initial time and plus this time dependent term. So depending on the sign in the parentheses, that this TW can increase or decrease. For Lorentz number, that is GL term is larger than GS term, so that this term is negative, so why this will decay. But for Lorentz number, that this GL term will become smaller than GS, so that this term is increases. This term will cause twist to increases. So we can use this simple idea to explain why helicity can have different behavior at different Lorentz numbers. But we want to comment that here we are assuming that helicity dissipation will follow these simple equations, but actually in the real case, helicity dissipation is not follow this simple equation, because that helicity distribution and vorticity distribution in the coiled ring are very irregular, and also that during this kind of compression and stretching, they have some helicity transformation between line and twist. Also here we are still assuming that the effect of thread, as you can see previously, that from DNA, a lot of small structures are wrapped around these rings. They can also have contributed to helicity dissipation. But this simple equation can somehow explain why helicity can behave differently at different Lorentz number. We can also confirm our findings by using a vortex link case. Here the two vortex rings linked together. The angle between these two rings is 30 degrees. The top row shows the evolution of the vortex link, visualized based on what is isosurface colored by the helicity density. You can see the evolution is quite similar to the Truffle cases, that the after reconnection form two rings, and there are some unreconnected thread to connect them, and they become diffused away. The bottom one shows the extracted vortex center line. You can see that it can well capture the evolution of these two, the initial vortex rings and the two rings after reconnection. Then we will show some topological quantity like link, rise, torsion, twist, and self-link. Initially, the link is 2, and at time t equals 0, all the rise, torsion, twist, and the self-link is 0. But during the evolution, that the rise will decrease and torsion, twist will increase, so the self-link remains conserved. And after reconnection, that self-link becomes 0, and the rise and torsion, twist abrupt changes in these two rings, but the sum, which is the self-link, is 2. So from this figure, it suggests that the total link, which is link plus the self-link, doubles during the connection from initial 2 to become each of the 2, so it's total is 4. So Right figure shows a comparison between h divided by gamma square and noise plus link. As you can see that during connection, noise continually increases. It suggests that this kind of increase of helicity, continually increases. This suggests that the increase of helicity is quite universal during the kind of unlinking and on-time process of what has not and link. We also find the noise plus link is continuous decreasing, and it continuously decreases. Just that during the connection, the link mostly converted to noise. And the difference, which can be considered as the twist, which will continue to increase Reynolds number. So that we expect that the effect of twist will play a more important role at higher Reynolds numbers. So here, with this one, we are trying to summarize some of our findings that we say that as the unit invariant, helicity plays a significant role in flow dynamics and energy cascade. In general, helicity is not conserved in viscous flow, even at high Reynolds number, which contradicts to most of people's findings. And due to asymmetric reconnection, helicity can rapidly increase, and this kind of increase will increase the Reynolds number. And the helicity evolution after reconnection strongly depends on initial configuration and also Reynolds number. For Reynolds number, it can decay, but for high Reynolds number, it can increase. And the sum of the link and noise continue to decrease during reconnection. This is consistent with what observed for quantum vortex knot and link. And the difference of helicity and the sum of link and plus noise, what we call twist, continuously increase with Reynolds number. So it suggests that it may play a more important role in helicity dynamics at high Reynolds number than this is somehow people always ignored. I think that simulation of cylinder vortex in viscous flow is very computationally expensive. So most of the results cannot be obtained without supercomputers. So we want to thank the support of our HPC department and the tech at University of UT Austin for their providing our computational resources. And also that we want to thank our colleagues for some collaboration and discussions. And for people who are interested in this talk, here are the reference that related to this talk. Particularly this our recent published annual review paper, which will come out next year, which already come out online, which will be published next year. And with that, I'm open for questions. If you have questions, you can ask us. And if you have some question later, you can email us, either email me or even email Fazle. Yeah. For now, I'm stopped the talk and I'm open for some questions. Yeah.
Yes, I've got a question about the Truffle Reconnection.
Mm-hmm.
In your picture, you start with the trefoil, it reconnects, and you get this two unknotted and unlinked circles.
Mm-hmm. Let me show
How many reconnection events did you have? I mean, with just one reconnection event on the trefoil, you'll get the hop link. With two, you'll get the hop link.
Oh, in our case, that's just three reconnections happens at the same time.
They happen simultaneous. Okay.
Let me show the picture here. Like here, there are three reconnections, just three simultaneous reconnections, like you show here, three happens at the same time. So after reconnection, directly from two rings. Yeah. It's different from experiment that typically is perturbed, so that was one reconnection to form a link, then another reconnection from two separate rings. Yes, it's quite different from here. Yeah.
Well, first of all, thank you very much to Professor Hussain and Dr. Yao, and of course, I welcome more questions from our attendees. Well, I have a curiosity, if I may. Jay, you mentioned the piece of work of Zhao and Scalo. And
yes.
Can you confirm from your data that that analysis holds and is indeed appropriate?
You mean this work?
Yes.
I found that it can be used to qualitatively explain the increased helicity, but it's not precise because in the actual case it's more complicated than what they show here.
Of course, it is.
Because they only assume that very simple cases, but in the actual case we find that this equation cannot be directly used to quantify the helicity increases. I think it just can be qualitatively used to explain the helicity increases. But I think that we still need to find a way to quantitatively to show, okay, how the helicity increases and what amount of helicity increase during reconnection. Yeah, I see there's some work we can do there. Yeah.
Okay, thanks.
I have another question about the Truffle Reconnection. And when you finish the reconnection, you get two rings, a big one and a small one.
Yes.
Do you always see big and small, or do they ever come out to be the same length?
Oh, they will not be the same length as we show. Let's show here that the length for the smaller one is much smaller than the larger one. Yeah. This is the length for the small. This is the length for the large
So you
one.
always get a small one. You always get a small one and a big one then.
It depends. I think it depends on the initial configuration. I think that Professor Rika or other people know that if you like for the initial condition, like we found that we also already know we found that if you change the lambda here, lambda controls the relationship between the large ring and the small ring. If you control the lambda, then you can control the ring after reconnection, how big the small one, how big the larger one is. Yeah. So that in this parameter equation, you can choose the lambda to make the length to adjust the length of these two rings after reconnection. Yeah.
Okay.
I think for smaller lambda that the length of these two rings become more comparable. Yeah. Maybe for large, I'm not sure. For large one, maybe become more comparable. Yeah. So, but I said you can use this equation to control the length of the two rings. Yeah.
Renzo, may I ask a question?
Yes.
Oh, sure, Gunnar.
So
go ahead.
this is maybe a more comment than a question. So regarding Renzo's question about the anti-parallel reconnection. So what we noticed is that you get always anti-parallel reconnection if you have isolated flux tubes. So if there's no background vorticity in your domain, your flux tubes are isolated tubes in your volume under consideration. If you have a background vorticity of one polarity, so of one direction, you can also get reconnection which is not anti-parallel. And we have done experiments in so-called vortex braids where we see that. So it is possible if you have a background vorticity.
It's quite interesting, but during the experiment, can you track that just before the connection, the angle between track the vortex line to see if it's anti-parallel or not? Because we also find that with the background that it can become anti-parallel, but just immediately before the connection, that at a local point that it's parallel, because if you calculate the vector of the vortex line, it's parallel. We have
if the background is too weak, it might still become anti-parallel. But if you have a strong enough background, you can also get reconnection without anti-parallel, without it being anti-parallel.
Gunnar, I am, of course, this is an interesting point. I don't want to dispute that, but of course, with background, with the superposition of other flows, you can, of course, interfere with the ideal situation of having, let's say, zero background flow and just focusing on the mechanism of reconnection. I understand that with the background flow you can, force or drive the angle and the mutual reconnection to different geometric configurations.
Even in the simple case where the background may have a preferred vorticity, so it will be asymmetric because it will add to the circulation of one and subtract from the other to start with. So many such combinations are possible. As in any situation, we try to first understand the simplest scenario first. And I totally agree that the anti-parallel is not required, nor even, of course, we all know, equal dipole. And some of our simulations, we suppress the asymmetry or symmetry breaking of the head-tail structure by only computing 1/2 of the flow domain or 1/4. But that's not same if you let the whole flow. There will be inherent asymmetry because the dipoles in the braid, in the thread, will not be symmetric.
That's correct.
Yep. I was going to comment because it's a good question that because we find that no matter like how the background vorticity will be, but before reconnection, it's always become localized events, so that it's always determined by the local vorticity. So that I assume that just before reconnection, so it's still anti-parallel. Yeah. So we have tracked the vortex line. We shows like the tangential vortex line. We find that it perform like 180 degrees. Yeah, just before reconnection. Yeah.
Maybe if I can ask another question.
Yeah,
sure, Gunnar.
So you showed various plots with the time axis T star.
Mm-hmm.
How does this is probably some kind of normalized time. How does that How does that compare with your dissipation time?
This is a good question. We haven't thought about that question. Yes. In our study, we haven't tried to characterize the dissipation time.
I would expect that dissipation time is much larger, but is it?
Maybe possible, yeah. Right now we just this is normalized by the geometry effect of the knot, yeah. So it's normalized based on radius, yeah. But we haven't tried to do a comparison on with the dissipation time, yeah. I expect that's much larger too, yeah.
Dissipation time is time dependent, so dissipation is time dependent. So how do you define dissipation time? I'm not sure I understand.
Yeah, relative to your characteristic length scale, let's say the diameter of your initial flux tubes.
Mm-hmm.
No, but what dissipation you use to get this dissipation time? Maximum?
Yeah.
Okay, yeah, that's fine.
Yeah, I think this is also a question that related to that. We found that initially most people assume that the twist will be rapidly dissipated, but we found that at Hurricane number the dissipation is much longer than we expected. Yeah. So I think that dissipation time, I agree with you, that's much longer than what we show, like for compared to our normalized time. Yeah.
Okay, thank you.
Okay, yeah, thank you. Yeah.
Renzo, can I ask a question?
Sure. Please, go ahead.
Very interesting talk. I had a question for Gia. I could follow, in fact, I was familiar with the work of Irvine, and the simulation that you showed on the Truffle and the reconnections were very nice. So I was wondering, is it obvious based on the insight that you have to predict what would happen if you consider, for example, a twist knot, so let's say for 1? Would there be anything interesting that might appear there? Because you consider a Truffle knot, which is a torus knot, it's also a twist one, but it's a torus knot, and you consider almost like an ideal geometry of your chain, where the environments near each crossings were, there was asymmetry obviously there. So if I go and consider for 1, where the environments would be different, could one be in for some surprises, or is it obvious what would happen in that case?
Actually, this is a good question. Right now, we are conducting some studies that similar to what you suggested, because right now we consider here that quite symmetric, but in the real cases, you can never get this kind of symmetric scenario. So we are trying to quantify that if there's some perturbation, that this knot will not be symmetric, and to see what will happen, and to see, okay, what conclusion we draw here will be universal, what conclusion need to be changed. But we find that this kind of increase of helicity is quite universal, because this is due to the twist generation during the reconnection. We find that no matter how you perturb that one, as long as the reconnection, you have generation of this kind of increase of helicity. Yeah. But how to quantify the perturbation effect, I think that is something that we are currently doing some research on that. Yeah. Because I think that it's very complex, and all the report here, all the result report here, I think that depend on the configuration, depend on the initial condition. If you change a little bit, lots of the conclusion may need to be changed. Yeah.
Well, if I may comment on that too, let's not forget that geometry is really the guy who's playing a major role here. So it depends very much, whatever topology you choose, it depends very much on the geometric configuration of the initial condition. That would trigger the evolution in one way or another. And I'm happy to remind us that in superfluid simulations of vortex tangles made by Carlo Berenghi, there are instances where let's say the topology can even increase at times. So if we think of some window, specific window of the evolution, not necessarily you always have a decreasing topological complexity, because indeed is just the complexity of the geometry that induces reconnections here and there, and you can well have an increase in complexity rather than a decrease. So it's totally open, I think, the path.
I see. Yeah. We also have some work on viscous cases of like the topological transition between like different node, different rings. We find that it can be very complex depending on the initial configuration. Yeah. This I totally agree with Professor Rika. Yeah.
Okay, if there are no further questions, well, thank you very much, Professor Hussain and Dr. Yao. Beautiful talk. Thanks.